In this video, we are going to study the specification of concurrent data structures, which is usually called linearizability. As the word suggests, the meaning of this linearizability is that all the operations on a single concurrent data structure can be linearized, or there is a total order among the operations that are just congruent with each other. So let me explain the definition a little bit more. But before that, I'd like to ask this question. So what should be the right specification of a concurrent data structure? So the concurrent data structure is much more complicated than the sequential data structure in the fact that multiple threads may concurrently access the same data structure at the same time. And the specification must be as simple as possible. And this specification, however, needs to take into account the possibility that multiple threads are concurrently accessing the same data structure at the same time, but nothing more. So the right specification, which must be simple for a concurrent data structure, is that its complication over the sequential data structure specification is that multiple threads may have a different order of operations. I mean, multiple threads may perform concurrent operations, and it should be the only complication over sequential data structures. It is the high-level idea to answer this question: what is the right specification? It must be as simple as possible, and as a result, the only complication of concurrency is the order of operations, nothing else. In particular, the order of instructions should not matter when analyzing or giving a specification to the concurrent data structures. The particular list of instructions doesn't matter. It shouldn't matter in the specification because the specification should be as simple as possible, and it is bad to take into account the order of instructions. It is very bad specification. So as a result, we are trying to come up with a good specification for concurrent data structures, and the golden standard of this area is usually called contextual refinement, which means that the concurrent data structures as if an abstract data structure, and in which you can perform operations on the abstract data structure without worrying about instructions. So these abstract data structures have an interface that is either push, pop, or other data structure operations, but it should be the case that at every time, a single instruction doesn't matter in the specification of this abstract data structure. The actual concurrent data structure have concrete instructions, and these instructions are actually executed, and it is the specification from the programming languages or architecture. But the specification of this concurrent data structure itself, they don't need to be related to single instructions. What we want is that the specification is that, it is working as if there is an abstract data structure instead of a concurrent implementation of these concurrent data structures. And this abstract data structure only have a few APIs, for example, push, pop, or iteration, or other kinds of high-level APIs, instead of concrete instructions that will be executed in architecture or program languages. And this contextual refinement means that the concurrent data structure works as if a corresponding abstract data structure. Even though CDS are implemented using concrete instructions, the specification is that they work as if its counterpart abstract data structures, for example, concurrent queue, concurrent stack, or things like that. And the linearizability, which is usually the specification for the concurrent data structures, it is just for a key lemma for the end goal, which is the contextual refinement. And linearizability basically means that, as I said, all the operations can be ordered according to some order. Here we are going to say the order is R. And all of these CDS operations can be ordered using this R. And the ordered operations are congruent with each other. So as far as this property is held, it is very easy to derive the contextual refinement. So now let's study the properties of this linearizability first. As I said, in an execution, there is a data structure, and there can be multiple operations on the same data structure. And to satisfy the linearizability, there should exist a total order, which I'm going to say R, among all these concurrent data structure operations. For example, if there are 5 operations, push, push, pop, 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 and then the R orders these 5 operations in some way. For example, it can be push, push, pop, pop, push, or push, pop, pop, push, push, or some just list of operations. Some reorderings of these operations. R is such a reordering. And furthermore, this reordered order R must satisfy the following 3 properties. The first thing is that, okay, suppose that a push operation happens before another pop operation. Then, in the order R, the push operation must be ordered before this pop operation. And this happens before is defined in such a way that if the view at the time that O1 is finished is smaller than or equal to the view that is at the beginning of this operation, then we're going to say this O1 happens before O2. So again, the definition is that O1's end view is smaller than or equal to the O2's beginning view. That's the definition of happens before. Okay, so far so good. And if such a thing happens, then it must be the case that O1 should be strictly happening before O2, as the view suggested. And it's the reason why we have to order O1 before O2 in the linearization total order R of this linearizability criteria. So one of the examples is that if a single thread performs 2 instructions, a push and pop, then the earlier push operation must be ordered before the later pop operation. So it is implied by the fact that the earlier push instruction happens before the later pop instruction inside a single thread. So if that is the case, then the push should be ordered before the pop operation. So this is the first criteria for the first criterion for the linearization order R here. And the second criterion is that in order for R to be a linearization order, then it should satisfy this property, which means that, okay, we ordered operations for a single data structure, and they should behave as if these ordered operations are acting against a sequential data structure. For example, you pushed 42 to the pop, and let's say that another pop operation is ordered after such a push operation in this linearization order. Then it must be the case that the pop should give you 42. You just pushed 42, so just right after pop operation must return 42. It should not return, for example, 33, because it breaks the sequential data structure specification. The operations in the order R must be acting as if they are acting on a single sequential data structure. Without this, we cannot say that, oh, this is a concurrent stack, because it doesn't act like a stack actually. And the third criteria is a little bit more specific to concurrency, which is that, for example, you push a value to the stack, and you pop the same value from the stack, then the pusher and the popper must be synchronizing with each other. And as a result, the push operation must happen before its corresponding pop operation. So suppose that you pushed 42 and another thread pop 42. Then there is a synchronization as if there is a release and acquire synchronization. Recall that release acquire synchronization requires that the release write happens before the acquire write by transferring the view from the pusher, from the release write to the message to the acquire read. The same thing must happen here. If you push a value and another thread pops the same value, then there should be synchronization as if there is a release acquire synchronization. And as a result, the view should transfer from the pusher to the underlying stack to the popper. So that is basically the requirement, the SYN requirement of this linearizability. So if an order satisfies these three properties at the same time, then that is a linearization order. And you can say that, if for an execution there exists an R that satisfies these all three properties, then we can say that the execution is linearizable. And if a program's all executions are linearizable, then we can say that, this program or this data structure is linearizable. In other words, an implementation of data structure is linearizable if all its executions are linearizable, and an execution is linearizable if there exists a linearization order for the data structure that satisfies all these properties at the same time. So that's basically the meaning of linearizability. So let's understand the meaning of this from a little bit high level view. At the high level view, the linearizability means that, there's an execution, then the operations on some concurrent data structure have resulted in some output. You push the 42 and you pop some value, you push value, you pop some value, etc., etc. You performed multiple operations on the list, for example, for stack. And what linearizability mandates is that the operations result, for example, returning 42, returning 37, etc., they should behave as if there is an underlying sequential data structure that serves the operations, and the value must satisfy such a property that all the operations are congruent with each other according to some stack specifications. So because this is so much close to contextual refinement, from proving from this to this, proving from linearizability to contextual refinement is not that difficult. So the right specification for CDS is contextual refinement, but in turn, it is really similar to linearizability. If you're interested in the technical details of the linearizability a little bit further, then you can consult this document that I wrote a few years ago. And this idea is basically illustrated with an example of a stack, if I recall correctly. So if you want to dig further about this, I refer you to this document. So far, so good. Okay, in the previous slide, we discussed what is the right specification of the CDSs, and we just said that this is the linearizability. And now the next question is that how to prove the linearizability in the presence of a concurrent implementation, how to prove the concurrent, how to prove the linearizability of the given concurrent data structure. So it is actually an active area of research even for now. So I don't have a decisive answer or definitive answer for this question, but there are a few wisdom that I think that you can understand even without knowledges on the formal verifications of these concurrent data structures. Okay, so in order to prove the linearizability, the first thing to do is finding the linearization order. The proof should begin with finding the linearization order for a given implementation and for a given valid execution. According to, for example, promising semantics, you need to find out the linearization order among multiple operations. And after that, you can use some logics to prove actually that the picked order is actually linearization order. And there are roughly two key ideas in finding a linearization order. Okay, the thing is that you first order write operations. For example, you push, pop are both write operations because you are actually modifying the underlying data structure. And you order such operations according to the order of compare and swap instructions. And we are usually going to say the crucial compare and swap instruction as a commit point. Okay, and we observe that many concurrent data structures, when they write something to if they modify the data structure, and they usually have a compare and swap or other kinds of read, modify, write atomic instructions. And one of the points is actually committing the operation. And we are going to say that is a commit point. For example, let's say for an example, in the stack implementation, when you push a value, then this compare and swap is the commit point. If you succeed in casting this head pointer, then you successfully push the value. Otherwise, if you failed in this cast, then it effectively means that you failed to insert the value. The same is true for this cast as well. When you succeed in a cast in the pop operation, you actually succeeded in removing a value. Otherwise, if this cast fails, then the entire operation of pop has been failed. You didn't succeeded in removing an element. So this cast and this cast is determining whether an operation is successful or not. And that is usually called the commit point. And the key idea for finding out the linearization order is that we order operations according to the execution order of these cast instructions. For example, if this instruction is executed before this instruction, and then the corresponding push operation is ordered before the corresponding pop operation. Otherwise, if this cast operation is executed before this cast operation, then the corresponding pop operation is happening before the corresponding push operation. So that is basically the key idea. So again, so in written form, the first key idea is that order write operations according to their commit point execution order. Recall that not all data structures have such a commit point. For example, the trace left queue I'm mentioning here, it doesn't have a single cast operations that is regarded as a commit point. For those kind of niche data structures, we need to find the linearization order a little bit differently. But for most of the data structures, for example, stack and queue and in the list, all the write operations that modifies the data structure, they all have commit points, and we can linearize the operations according to the single instruction commit point. Okay, and let's move on to the second idea. The second idea is that, okay, we have ordered those write operations that modifies the data structure. But how about the read operation? For example, a stack or queue may have isEmpty function that checks whether the data structure is empty or not. It doesn't modify the data structure at all. It just checks whether the data structure is empty or not. So we cannot apply the first key idea to such operations. It doesn't modify at all. So if that happens, then we can do some heuristic. That means that if a read operation is a reading from a data that is written by some write operation's commit point, then we can order the write operation just before the read operation. So we are interested in from where this read operation reads from. And we can just insert the read operation right after the corresponding write operation that writes the value that is read by this read operation. Usually it works, especially isEmpty in the stack and queue can be easily linearized in this way. And you can immediately understand why this should be correct. It should be correct because the result of this isEmpty operation, isEmpty method, is determined by the read value, and the read value is determined by the value that is just written by the just previous write operation. So it is very natural to put the read operation right after the write operation. But as I said, there are a few data structures that doesn't have the commit points, and also it is a little bit unclear how to put read operations among these write operations. I mean, I set a general rule of thumb or general design criteria, but it doesn't explain everything. So there are some cases that it is a little bit difficult to pick the corresponding write operations for a read operation. So if that happens, we need to think a little bit more about this, but that is beyond the scope of this lecture. So I'd like to, if you're interested in this kind of topics, please contact me to study further about the linearizability of data structures. Okay, so far so good. And I'd like to move on to the examples here. Tribal stack. The data structure order is the order of successful CAS. As I studied just before, push and pop operations are working on the same head pointer, and the order of the successful CAS operation on the head pointer is the linearization order of the tribal stack. On the other hand, the microscas queue, it is a little bit more complicated because its operations work on different locations. But it doesn't matter. Regardless of there are only a single location or multiple locations, the operation order for microscas queue, the push and pop orders, is the successful CAS. So if a push operation performs a CAS before a pop operation performing a CAS, then they are ordered in such a way. But recall that in microscas queue, we are helping the others by updating the tail pointer. So the tail pointer, the cost on the tail pointer, it doesn't matter for the operation order because it is not the commit point. The commit point is always on the head pointer or the next pointer. And the order of the costs on those head and the next pointers is the operation order, and the order of the and the costs on the tail pointer, doesn't matter in the determining the order of the operations in the microscopic queue. Harris list is a little bit more complicated, and as I said, the right operation orders is determined by the order of successful CAS or fetching or instructions on the head and the next pointers, and it is almost the same with the microscopic queue. And also, we don't need to take into account the detachment of the logically deleted node inside the Harris list, because it is for helping the other threads. It doesn't consist of a commit point. So that's the reason why we need to determine the order of write operations in lists, not with the detachment of the logically deleted nodes. We only need to consider the successful CAS on the head and the next pointers without detachment of the logically deleted nodes. But what is more complicated in this list is that the read operations order is really difficult to even specify. Suppose that there is a insert or removal operations from the list, and suppose that there is a concurrent traversal of the linked list, and this traversal is effectively a read operation, but it is really difficult to figure out whether this read happens before a concurrent write, a concurrent push, or concurrent removal, it is really difficult to determine the order among those two, because it may be possible that even though the execution of the detachment is executed before removal, it is possible that the read operation, the traversal operation, may read the stale value that is already overwritten in the shared memory. But it can read from its own cache, so it may read a stale value that points to the already detached node. So such a kind of complication is not yet resolved completely in the literature, in the academic literature. So it remains an active research area even to today. So actually, your TA, Jae-Hwang, and I are actively working on this kind of giving specifications for data structures and the underlying garbage collectors. So if you're interested in this kind of research, please contact me so that we can discuss further about this kind of research projects. And furthermore, I only set the linearization order today, and the remaining things to do is that actually proving the linearizability for the execution. Given an execution and given a linearization order, you need to actually prove the three criteria for the linearization order about the view and the sequential specifications and the synchronization. And this video is a very brief tutorial on how to do that. So you're not required to understand every details of that, but I hope that you can grasp the general feeling of what's going on in actually proving the linearizability of a data structure. So this is a lecture given in the last year, and as a requirement for on attendance, I will require you to watch this video as well as this video as well.